Yeah,
welcome to the AI show. I'm Scott Stevenson, co-founder of Deepgram. With me is Jeff Ward, a.k.a. Susan. He's a Navy pilot, acclaimed dad joke writer. We've never had you give a dad joke. We need to do that. Acclaimed dad joke writer.
Oh, yeah. Well, okay. Knock.
Who's there?
Spell.
Who?
WHO.
Oh, good one. That's a real good one. He's also an AI scientist at Deepgram. On the AI show, we talk about all things AI. What is it? What can you do with it? How does it affect you? Where is it going? We're live and ready to answer your questions. Comment on YouTube and Twitch or tweet at Deepgram AI to join in. Today, we're asking the question, our big question, how is machine learning or deep learning affecting science?
Actually, I'm asking the question of you.
Good. I'm ready to answer. What's the question?
For those that do not know, Scott here has a little bit of a science background.
Little bit.
And a little bit of machine learning and science background.
That's true, yeah.
So Scott, can you at least give us the 10,000 foot overview of a little bit of what you've done?
10,000 foot overview is I have a PhD in particle physics, and I was Dr. Scott. But I was searching for dark matter deep underground in a government-controlled region of China, basically a James Bond lair.
I like it.
Yep. We had to design the experiment and build the experiment, operate the experiment, take data, analyze the data, write a paper, So this is what you do in experimental particle physics. And we did that searching for dark matter. And we did it with lots of computers, servers, CPUs, things like that. Lots of copper, plastic, liquid xenon, cryogenic stuff. And the CPUs were used to do data analysis, and we were using like boosted decision trees and neural networks and other standard like statistics-based cuts in order to figure out, was it a dark matter particle or not?
So tons of signal noise search, basically.
Yeah.
Right?
These detectors are little cameras, but the cameras that have no lenses, and by little I mean they're actually big.
I like that.
They're maybe a meter by a meter, but the pixels are maybe a few inches. So they're really large pixels. But these pixels can sense individual photons, so a very, very small amount of light. Yeah, but there's a few hundred of them essentially, and you have to pick out what happened inside the detector based on the pattern that is in those pixels. No lenses. Again, you can't like zoom in and see the particle was right here and I can see its hair, but you can say like within a region about this big, the particle interaction happened, and it was also had a flash that was this size and things like that.
But basically your machine learning techniques were attempting to take that huge amount of data and shift signal to noise in an efficient way from it.
Yep. So coming out of the PMTs wouldn't be it would be a digitized signal, but it would look like a waveform. So, it kind of looks like an audio waveform essentially. And those signals were different for every type of particle interaction. But the two main types of particle interactions are, what's an atom made of? It's made of a nucleus and some electrons, pretty much. At the energies we're talking about, they normally don't like blow apart into smithereens. It's either the nucleus gets hit or the electron gets hit. And if the nucleus gets hit, then the whole atom starts like ripping through and generating photons, electrons, and heat. And if an electron gets hit, then an electron goes ripping through. And when that happens, the signals are different. They give off different amounts of light. The size of the light, or just the size of the pulse they give off, is different as well.
So for anyone that is interested in why these dark matter or even neutrino detectors are so big, but also always full of some fluid, it's because you have to see the light that happens off of that interaction. And if it wasn't some sort of clear fluid to the light that's coming off, or clear medium light coming off, you wouldn't be able to see it.
Yeah, lots of things scintillate, but many things are not transparent to their own scintillation light. Yeah. And so, hey, if you throw particles fast enough at things, light will be made.
A lot of
light.
But
you won't be able to read it.
Yeah.
And that's one special thing about xenon, is that it's very clean. It's not radioactive, or at least not very radioactive. And it's transparent. It scintillates, and it's transparent to its own scintillation light.
So that gets back to our question. The question is, machine learning, how is it impacting the sciences?
Yeah.
And your own experience shows right away how the recent world is being impacted by this. Obviously, dark matter, the search for what is that missing? What is it? 95, 97? What's the right percentage?
80%
ish. Some large amount of the universe we can't really figure out what's going on with.
So that's like dark energy, and then matter is like 20% or so, and then there's like 4 or 5% that we actually know
about it, doctor?
Yeah.
But no, so that is an excellent example of where we're seeing some big impacts from machine learning.
The huge thing that we saw was that we could do a lot with a small team. So you could take billions of data points, you could collect data, and a team of 5 or 10 people can actually analyze the data. Whereas if you look at teams at the LHC or CERN, which are these really big particle colliders, so we have a particle detector, but it was looking for astrophysical particles. So you didn't have to have a collider, you didn't shoot anything into it. The universe is already shooting stuff into it, essentially. But if you have a collider, then you actually make the particles that then get shot into the detector and then read. So this is like the LHC, CERN, Atlas, those types of things. But that's happening in Europe, and there are a few other ones around the world. But nevertheless, those were started like in the 60s, 70s, like those type of colliders. And they've been using the same techniques from way back until the 2000 teens, essentially. They tried to do machine learning. There's actually a story here. They tried to do machine learning back in the second AI boom, which is the 80s, essentially. And they're like, oh, neural networks, et cetera, right? And because we have this problem, can we tell signal from background? Let's train a machine learning model to do it. Well, there was some good that came out of that, but for the most part, everybody got super burned in the particle physics community, and they were just like, neural networks suck. They don't do what we need them to do. And really what it was, our computers suck and we don't have enough data, and we don't really know how to train them all that well, right? But then fast forward 20 years, and our computers don't suck anymore. We have the data and we know how to train them now, you know? And so essentially that was like the 2010s onward. There were physicists around that were like, wait a minute, machine learning, it probably can help us a lot. And I see all this repetitive stuff that's happening, thousands of scientists in this experiment trying to pick which cut we should make or something like that. And it's like, why don't we just have computers do it?
Do that initial sift,
Yeah, and so this is the big thing that we did is we can have tons and tons of data and we can do some complicated analyses, but we have to do it with machine learning because otherwise it would take too many people.
Yeah, it's amazing. I think the other bent on that same note though is efficiency in processing. Have you seen the stuff going on with like protein folding? I mean, huge processing advances going on just because they're using deep learning models, or they're using machine learning models to accelerate, the guess at what that protein will fold into, So for those that don't know, there's like, the challenge is you've got a whole bunch of atoms that are strung together in this big complicated molecule. And when you let them go, they all kind of fold and convolute into this weird shape. Yeah. And that weird shape is the point. Right. So,
if it's not in that shape, it doesn't do its job.
Yeah. Your cells let through like a shape. And if you can figure out the shape that something's going to snap to, you can maybe design a drug that'll enter a cell that another one wouldn't, or something along those lines.
Or like make proteins actually stay in that shape for longer.
Exactly. So if you can predict how proteins are going to fold, crinkle up and do all that stuff, you can do some really good stuff. But it's really hard. It takes a lot of computational power.
Yeah.
And machine learning is coming along and making it more efficient.
Yeah, it used to be just grid search, just use flops, lots of computational power.
I like the flops.
Yeah, it was distributed. I remember doing this actually. Yeah. I have a PlayStation 4, a couple of PlayStation 4s, maybe 4 or 5 or so, in my kitchen, or no, actually in my living room and my kitchen, crunching numbers to do protein folding, for free.
Yep.
Before I was in graduate school, because I just thought it was so cool, right? Exactly. It's like, hey, you need computational power in order to do this problem. I'll help you with that.
A spin-off of SETI at Home, right?
Exactly. Yeah.
So
like the first well-known crowdsourcing of your own computer stuff before Bitcoin mining.
Yeah, before Bitcoin mining said, like, well, you can make money, so forget all those free altruistic purposes. We don't care if you want to look for aliens or help, find the cure for cancer. You can make money.
You can make money, so let's do that. Yeah.
No, that's awesome. So are there any other good examples of, like, improved computational efficiency or great, like, new designs coming out of the machine learning world?
Yeah, there's the good story about the redesigning your tokamak.
Oh,
so it's like fusion has been a thing for the last 60 years. Fusion. That's the real new power.
It isn't the running joke about fusion? It's 50 years away.
Yeah, well, the running joke keeps getting longer. It's always 20 years away, but I like that.
Away. There we go.
But I like
20
that.
years ago, it was 20 years away. 20
now
years.
It's 50 years away. Yeah, but it's only 50 years away. Yeah, but it's probably a lot closer now. And actually, this is something that's really interesting to me too. It's like if you give the world really cheap power, then you make the world much more productive and you don't destroy the environment.
Hopefully,
And so, I mean, we'll always find ways to destroy the environment, but you don't destroy it as quickly.
Give me a challenge, Scott, and I will take that challenge.
But it's a really hard, complicated thing to build some of these detectors. And they said, we've tried many things over the last 50, 60 years. And spent many billions of dollars trying to build these reactors, and we've gotten pretty good, but they're still researchy. They're still not able to be turned into a real one that actually produces power on a large scale for all of humanity and things like that. Let's throw machine learning at the problem and see what happens. And then now there's talk that these designs are like actually able to be built and probably will
what was the last
serve
one?
the purpose.
It was. I thought that they reached some milestone, like 100 seconds or something like that. Like there's so many challenges going into confining so high of energies, right, in such a small space.
Yeah, the trick with fusion is that everything is a gas pretty much, and so it's really easy to cool it down. Well, there's not much mass there, right? But there doesn't have to be a lot of mass because there's a lot of energy if you can convert convert even a small amount of that.
Something
mass.
about energy
equals
mass,
MC square or something like that. Yeah, but if any of that gas touches the wall of the reactor, then it's instantly going to be cooled down, essentially. And so it's like, how can you contain it without touching it? And so they try to use magnetic fields, but there are some tricks with that. Basically, that it doesn't work so well. That's why it took so long. And like it's probably the only way to do it, but and you can kind of work out that it'll probably work, but the problem is like making it in practice. And so machine learning comes along and says like, hey, actually, we have a design that might be able to be built and serve the purpose that you need.
And it's all about the hyperparameters and something like that. So when you think about a tokamak, this thing that's creating a plasma and squeezing it really tight and all that, the field you have to create is really uniform, but at the same time, there's practical constraints on this. Like, where do you put this pipe? And how do you put these wires?
Yeah, you have to cool it. You have to cool it down so everything doesn't melt down. So, how do you design it all?
So there's all these gives.
When it heats up, it's gonna crack or something.
Exactly. There's all these gives and takes in the design. Like everything you do may affect how pure that magnetic field is, but at the same time, if you could route this pipe a little bit better, you could get a lot stronger field, so it doesn't need to be as perfectly this, that, the other. So that's where things like machine learning can maybe help search a big, huge hyperparameter space. That it's just really impossible in other
humans
ways.
typically rely on symmetry to guide this. It's like it's got to be circular, it's got to look nice, it's got to whatever, and a lot of that comes from you can calculate the math pretty easily on whether it'll actually work, or it's easier to produce, or it's just I can only think of so many things, and I want to think of 15 different designs. Well, they're all going to be pretty symmetric, even though they can be symmetric in all these different ways, essentially. But a machine learning model doesn't care so much about that. It cares more about the task at hand, and it's like, I don't care if I put a pipe here if I can build some way to like get around it without affecting things. And that complexity can deal with the complexity a lot better than a human can. It doesn't have to. It'll still tend to, but it doesn't have to fall back on symmetry in order to make it simple.
We talked about this in a prior podcast, but at the core of any good problem is defining the problem. And honestly, when you say things like, people care about symmetry, and it affects the end result, but machine learning only cares about the problem. That's really a big core thing that I think machine learning might be bringing to the sciences, is really making people focus on super incredibly hardcore defining your problem and how close you are to a solution, as opposed to just jumping to ways of fixing it. Right.
Yeah.
So
it suffers a little bit from the like solution, or in search of a problem.
Yeah.
Kind of way of looking at the world. Where if you come from the other way, I'm just defining my loss function, and I have these things that I can do. I can put steel here and plastic here and this there, and it's like I'm gonna just exhaustively go through and try and figure it out, and then a machine learning model never gets tired.
It never gets bored of trying. The next step is 0.0001 different than the last step.
Yeah, but it's excited about that.
Yeah, excited.
It's like, this might make it 0.001 better. A human doesn't get that excited about
Not at
that.
all. And I bet you the results, the recording gets a little bit sloppy after this.
Yeah. Once you see the 80%, getting to 90% is real hard. And after that, everybody's checked out. They did their duty.
Yeah. Doing a grid search by hand.
Yeah.
You really realize how much machines can help us.
People used to do this back in the day too, like pencil and paper, and like when they would talk about let's do the calculation, it's like we spent weeks on this calculation. It's stuff like that.
Yeah, well, the hard stuff is actually hard for a reason.
Yeah,
and it's what needs to be done.
Yeah, you're always finding the boundaries of what's possible, and then spending weeks on the problem. Basically, when you don't have a calculator, well, that means you're writing down stuff and trying to figure out the answer. When you finally do have a calculator, okay, now you're trying to. The calculation part is quick, but the complexity of calculation is now problematic, and so you start doing things that you're going to want to program a computer to do, but you don't know that yet, and then computers come along and you're like, oh, thank God, now you've taken away a lot of this complexity, etc. But then you find a new problem to spend weeks on, and that's just how research works.
It is. So we're really seeing we've talked about a couple really important things here. Computers are helping us sift through data in ways that used to take huge teams. They're also reducing the computational costs associated with things like the protein folding that we were talking about. We're getting really good efficiencies there. What else is out there? Are there big brand new? Is it enabling something new or freeing up researchers to do things that they could never have done before?
I think it's a new skill. Unfortunately, hi researchers, you're gonna have to learn a new skill. And it's as if learning calculus and computing and all these other things wasn't enough. Here's another one, but it's a very powerful one, and it's one where you don't have to be the one that is smart about what exact little details you need to do in order to accomplish this task. All you have to be smart about is putting the constraints in and saying stay within these boundaries, and here's some training data, and then try to tackle that task. And not everything is going to be able to be done that way, but there are going to be a lot of things that are going to be able to be done that way. And so it's a new tool in the tool belt, and people are going to start thinking about the world and their problems, and just like they do with programming and math and statistics, and how can we uncover a new thing? And not everything is going to be machine learning. Not everything's going to be deep learning. Not everything's going to be statistics. You can learn new things just by writing, and you don't have to think about statistics, right? But that's really what it's going to be, is a new honed, sharpened tool, is a machine learning, create data sets, use models, turn cranks, get results, and go after the problem that way.
No, I totally agree. I had an argument with some friends a while ago. Not an argument, a discussion with friends. A friendly discussion.
A discourse.
Where I was saying all the sciences and all the fields, and the idea that we have a machine learning degree path, maybe we need to fragment that and saying you're in paleontology, there should be machine learning in paleontology, right? There should be machine learning in archaeology. There should be machine learning in all sorts of different fields.
Yeah.
Because just like, basic stats and from the math point of view, you go out there and you do, really good math in whatever field X.
Yeah.
Now machine learning is, related, but it's a new set of skills. It's
Yeah.
like you said, honing those data sets and understanding how to churn them through a good model. And all that
Unfortunately, this is one of the downsides to like higher education, meaning like graduate school plus, et cetera, that type of thing, research institutions. They don't necessarily have a good track record of taking in things outside their field and utilizing them really well in their own field. Some might describe their pace as glacial in that.
Progress is made one death at a time,
exactly.
right?
Exactly. Progress, is made one funeral at a time.
You're one funeral at a time.
Yeah.
You're right. You're one funeral at a time. Sorry.
Exactly. But so that's a long time scale. That's 50 years or so that you have to wait for your professors to die. But for instance, computer programming been around for a while now. Some might say 50 plus years, at least in a from a utilitarian perspective, from a real practical perspective, at least 30. Right? Mm-hmm. If you go to where particle physics is like, there's a lot of programming that you have to do. There's no like programming for physics course. There's no whatever. You're just forced by trial by fire to like learn the stuff you need to learn and move on. And same thing with machine learning. The same thing with engineering or CAD drawing or any of the stuff you have to do. It's kind of sprinkle a little bit of money, enough to live. Put you around enough other people that are making a similar amount of money, and like sort of mix it all together and say like, go create stuff. Those other people are graduate students, and then you do some search by graduate student descent, gradient
like
descent to find
grad descent.
Yeah, grad descent, exactly, to find a solution to a problem. I think that is going to get an overhaul. I think it's going to have to because of MOOCs, online courses, learning, etc. People are going to start to gravitate to these like canonical courses that are actually really good. There probably will be like an online course that's machine learning for physics or machine learning for particle physics or machine learning for biophysics or machine learning for whatever. Those are going to crop up in the next 20 years, and the whole model is going to change, and people actually will be good at those things, and they will have a real sharp tool belt rather than just like a dull one, which is kind of the case now.
No, that's awesome. I mean, I think we're seeing as machine learning filters into other fields. Medicine is also an amazing example of this. We're seeing just when it hits, it is a brand new set of tools which allows people to think in brand new ways and attack old problems in new ways and get fresh insights on them.
Yep.
But they have to recognize that that this is a brand new world they're going into and start
and it'll take time.
Those tools.
It'll take time too. I mean, even if you said, I'm going to drop everything and I'm going to start doing machine learning in my field, year one you might make. I wouldn't even say that you'd make enough progress to make a contribution.
Yeah.
You just kind of like maybe broke even,
A recognized contribution.
Yeah.
You're making a contribution. But will your contribution be recognized?
Yeah. No, the real contributions are going to come in like year 3, 4, 5 when you're like, whoa, okay, I just got effective at using this tool.
Yeah.
And that's a hard time scale for people. If you can't learn it in a week or a day or an hour, then you have a big drop off. And you have to have a big impetus to keep going. And people around will see that, though. They'll see the success of other researchers, papers, et cetera. They'll be using them. They'll be citing them. They'll be like, man, okay, I really got to do it this time.
Yep. This time I finally have to break down and this new tool that really seems to be breaking open those problems, that my field couldn't crack before. But now, we've got good results.
And at least from what I saw, people get a little tired of learning so many different things, and this is kind of problematic, but also a good thing. In machine learning, you can kind of forget a lot of it and just go down the path and learn along the way, and then like revisit those or something. So like, what exactly is a hidden Markov model? What exactly is just all these things that people used in the past? And instead, you're using your CNN to find stuff or whatever. Yeah. But then you see references in the literature about it, and you figure out how it works and whatever. But you're learning it from a different context. Yeah. You know, you're learning it from a different view on the world, and that'll have its pros and cons. But that's definitely happening now. Like, it's been around long enough for that to happen. People don't necessarily know the old techniques anymore.
Yeah, but that honestly, that's the difference between someone that is not specialized, that is a machine learning scientist, and trying to develop those basic techniques and those basic concepts, and someone that's combining it with a field like physics and machine learning together. Right?
Applied AI,
into the field of physics, which is also probably why those fields need to embrace it and start specializing the curriculum and making it part of it, right?
Well, I think there's a little love affair here, similar to like math and physics and chemistry and physics, and math and chemistry and astrophysics and just astronomy and that sort of thing, where they feed off each other, and you learn a lot in a certain area because tools became available, resources became available, people are interested in it. Let's go like nail this, right? And then you go do a really good job on that. But then the other one has kind of been left to rust for a while, but then you come back to it. And this is definitely true of astronomy and physics, essentially. Astronomy happened, right? It was a big deal. The moon, Jupiter's moons, things orbit each other, etc. Back in the 1500s, that was still like a cutting edge thing, right? Move forward, 1800s, still like a big deal. 1900-ish, Albert Einstein time, like physics really took over. Thermodynamics is cruising, quantum physics, all this nuclear power, whatever, and MRIs, stuff like that. And but then around mid-century, astronomers who are kind of being poo-pooed go out and notice some weird stuff happening in the universe and discover dark matter and discover dark energy. And all of a sudden, physicists are like scrambling, to be like, how do we describe this stuff? We didn't know about it because we were too busy like looking down here, at a really tiny stuff.
And you've got the biggest physics experiment in the universe.
Yeah.
The universe.
All around you.
Look around the cosmic background radiation. How is that all lined up? Does that tell us something about quantum mechanics?
Yep. And a similar story with like quantum field theory in physics and math and theory of knots and stuff and strings coming back in math and physics and that sort of thing. All these things tie together and they feed off each other. And so I think there will be contributions from the applied AI side that are actually fundamental contributions in machine learning as well, and there already have been. But,
I think so too. I mean, especially we've already obviously seen this, and the medical field, studying the brain has made contributions in the machine learning, huge contributions in machine learning, and vice versa. Reinforcement learning, talking about potentially how parts of the brain works and back and forth. And like you said, other fields we're going to see those same things coming out of it. And that's what's super exciting about this. When you start pushing it out into the sciences, you get incredibly brilliant people that are brilliant in ways not exactly the same as
they factorize the problem a different way.
Yeah.
And then you get a benefit from that. Like, whoa, if you think of it that way, then the world becomes really simple. And so you can jump to different ways of thinking to solve the problem however you need to.
Plus, from the machine learning standpoint, we're like, I gotta beat those guys.
Yeah.
I can't let someone, dealing with dinosaur bones come up with something new.
Yeah, exactly.
I've got to make that first. So you get a competition going. And,
it's good.
And
get the blood pumping.
Yeah.
Speaking of getting blood pumping, you made some delicious bread this week.
I did. Oh yeah. Bread is.
Speaking of evolution and machine learning or just learning.
Yeah. There's a great recent article, a blog post I read about machine learning being applied to bread starter evolution and all that. This guy did a really great job of setting up, I think it was like scikit-learn, I forget exactly the tools he used, to watch as the yeast would rise and fall.
So it's like a camera?
Well, he had a camera set up, right? Like on his little tubes of starter, and he would feed it and figure out the exact times that.
So he wants to find a really good yeast. He wants to breed a really good
So
yeast
if you're not
strain.
into making bread, there's people,
not as much as you.
people have their starters. I had a starter for about 2 years, and I had to give it up when I moved. It would have been really hard to explain on an international flight why I had this jar of clearly biological matter coming out
That
of
you're
plane.
trying to keep
Is
warm
it a
and
liquid?
alive.
I don't know. It's starter. Anyways,
It's
so
food.
I had to give that up. So people get into their starters, and he was talking. This blog post was amazing. It was talking about cultivating wild yeast and trying to grow it, and like what's the optimal feeding schedules, and what's the optimal this and that.
Like, should you starve them for a while or give them as much as they want to eat?
Exactly.
Or cool them down and shock them with heat?
But it really showed, like, first of all, a good scientific method at play. Second of all, using machine learning tools to help aid those experiments. It was mainly on the measurement side, but you could see a lot more that could go into this. But it really shows you what machine learning can do. Just recognizing basics of how quickly this is growing or versus not. Those data points and collecting those data points for future analysis. Great stuff there. Like, the citizen scientist world that's being enabled by machine learning, by taking out a lot of the complexities that you would have had to have done by hand.
A lot of these things were impossible a decade ago, certainly 2 decades ago.
I'm not going to watch my tube of starter grow, take measurements every 5 minutes for 3 days straight. But if I can,
a machine can do it.
A machine can do it for me. And before good image recognition and all that came along, how are you going to do that? So there's great stuff, and then just other awesome sciences that are available with all the stuff that's done with all the ImageNet models that have come around. You can set up a camera and start classifying stuff that goes by your window. And do a lot of great citizen science with all that. Again, something that would not have been possible before. You can spend a weekend designing and building something, taking some off the shelf stuff, and classify all the flying objects by that come across, and do some basic science on what's flying through your window.
Many things are all coming together at once, and it's also definitely true in a lot of these areas that you're sort of limited by data as well. But you can collect data yourself, right? And this is what the experimentalists would have to do anyway, right? And they're not going to do it at a much bigger scale than you could, and you might even do a bigger, better job. So like, actually, you're at the cutting edge.
It's amazing what these technologies are enabling at every single level. We talked about fusion at big energy levels, searching for dark matter in the universe, all the way down to improving your sourdough round, to make it a little bit better, bread for you.
Have better eyes, bigger holes in it.
All sorts of amazing stuff that you can do with this. I mean, I'm excited for machine learning and the sciences. And
we'll have to revisit this. There are a lot of topics, I think.
Oh yeah. We could go down it for many hours.
All right. Well, that's it for today. Thanks for joining us on the AI show. What questions do you have about AI? Comment on YouTube or Twitch, or tweet us at Deepgram AI. We're Scott and Susan from Deepgram.
Certainly not robots.
And we come in peace.
Yeah.
See you next time.
Cheers. So, we were on a staring contest.